This is Dan Abbott. I'm making this short video for my students in the mechanical design class at Southern Maine Community College, and I just glancing at the camera realized I still have my SMTC hat on. We were at one time Southern Maine Technical College 20 years ago, and I love the hat, so I'm just going to keep it on. So we have a drawing of a pin. That's the one in the middle. The pin has a diameter of 15 at least material condition, 20 at max material condition. That's a way bigger range than you would ever have on a pin like this, but I want to visually show something. It has a straightness tolerance of 0 at max material condition, and then the maximum variation is 5, which would have to be anyway, but I'm using that just to demonstrate that that's possible to put on a print for the students. So what I want to do is to demonstrate what it means for a pin or any other part to have a virtual size, as opposed to its measured size. So we have a condition here and a condition here, where the pin's measured size in this case is its maximum material position size of 20. I've also got it bent by 5 millimeters. Down here I've got a pin and its measured size is 15. It is also bent at 5 millimeters. The virtual size is the distance from here to here, which is the two numbers added together. Now, if the measured size were, say, 18, that would be 2 millimeters away from max material condition, so now the straightness variation would be 2 as opposed to 0. Down here, the straightness variation would be 5, which is acceptable. Up here, it would be 0, which is impossible. So what does this look like when you actually start putting pins into holes, and what is the virtual size? The virtual size is the size the pin could be if it were perfect and still go through the hole. So let's go in the situation where this one has a measured size of 20 millimeters. The hole is exactly 20 millimeters. If I put that through there and then I go and say let's do an evaluation and an interference check, I check for interferences, there's no interference because that pin is perfectly straight, which is not possible. Now I have a pin that's not perfectly straight. I have a pin that's bent by 5 millimeters. Will it fit through that hole? Just touches at the top, just touches at the bottom, goes through the hole. If I do an interference check now, still no interference. The virtual size of that pin is 20. The combination of its measured size, 15, and the extent to which it varies from straightness, which is 5. You add those two numbers together and get the virtual size or the virtual condition, which is the condition that you use when you're designing to determine what kinds of tolerances to apply to whatever part you're creating, both linear or geometric tolerances. Over here, I've got the 25 millimeter hole. So I have the same 20 millimeter pin. You can see plenty of room for it here. This one is the same 20 millimeter pin. It goes through here. The virtual condition of that is 25 millimeters because now you have no interference. I calculate that. So the idea is that this virtual size is the size it would have to be if it were perfectly straight and still go through a hole of a specific size. So here the hole is 20 millimeters. If that were perfectly straight, it would have to be 20 millimeters. It's not perfectly straight, it's bent. So its virtual size is still 20 millimeters because it's bent 5 millimeters. 15 plus 5, 5 millimeters. Virtual condition on a hole is the other way around. Still the combination of how straight it is and the size that it's manufactured. But when you take the size that it's manufactured and the variation from straightness, instead of adding them together, you subtract them because a hole that is no longer straight is virtually smaller than a hole that is straight.